In this video, we're going to calculate the curvature of the given vector function, and we're going to find the curvature as a function of the parameter, assuming that the parameter is greater than or equal to 0. There are two main curvature formulas that we use. One of them is mag unit tangent vector's derivative divided by the magnitude of the derivative of the position vector function. The other main formula for curvature that is commonly used is the magnitude of the cross product of the first derivative and the second derivative of position, and then divide that by the magnitude of the first derivative of position, quantity cubed. We're going to use this version of the curvature formula, although this one would also work. So let's recall that the unit tangent vector can be determined by looking at the derivative of the position vector and then divide that by the magnitude of the first derivative. So the unit tangent vector is a unit vector in the direction of the tangent line. So let's calculate the first derivative of the position vector function. Now, we'll be differentiating each of the individual components, and some of the components have a lot going on, so let's give ourselves plenty of space. And the derivative of the first component is just going to be 4t. The derivative of this next component is going to be derivative of sine is cosine, and then we're going to subtract the derivative of this product, which is the first times the derivative of the second, derivative of cosine is minus sine, plus the derivative of the first times the second, and that completes the product rule and completes the derivative of the second component. Now the derivative of this third component, derivative of cosine is minus sine, plus a product rule here. And so I'm actually going to move this down to the next line to give myself plenty of space. So we have the first times the derivative of the second, derivative of sine is cosine, plus the derivative of the first times the second, which is going to be 1 times sine t, close the product rule, close the vector. So let's hope this simplifies. We get 4t from the first component. Now for the y component, we'll have cos t, and then distributing this negative, we'll have minus t sine t, but times this negative is going to be plus t sine t, and the negative distributed to the next term is going to be minus cos t. So that's our second component. The third component is going to be minus sine t plus t cos t plus sine t. And we see that we do get some cancellation. We have cosine t minus cos t minus sine t plus sine t. And so our derivative vector function becomes 4t, t sine t, and t cos t. So we now have r prime. In order to complete our computation of the unit tangent vector, we'll need to take its derivative, we'll need to calculate its magnitude, and then divide r prime t by its own magnitude. So the magnitude of r prime t is going to be square root of 4t quantity squared is 16t squared, plus t sine t squared is t squared sine squared t, plus t cos t squared is t squared cos squared t. So we have 16t squared under the radical. If we factor out the t squareds here, we're going to get t squared times sine squared plus cosine squared, which is 1. So this just becomes t squared times 1, or t squared. So the magnitude of this derivative vector function is the square root of 17t squared, and back at the beginning there was the declaration that we were assuming t was a positive quantity, which means that the square root of t squared is just going to be t, and there's no need for absolute value bars around that because the t value itself is already positive. So now to find the unit tangent vector, and as a reminder, that's r prime over mag r prime, which means we're going to take this derivative vector and divide each of the components by square root of 17 times t. So we get 4t over rad 17 times t as the first component, t sine t over rad 17 times t, and the z component is t cos t divided by rad 17 times t. And we see all of these t's are canceling out. So we have our unit tangent vector that does depend on the parameter. It depends on where we are along the path C. And this vector function is 4 over rad 17, sine t over rad 17, and cosine t over rad 17. So let's just check back in. Remember, curvature is going to be the unit tangent vector's derivative. Find its magnitude and then divide that by the magnitude of the first derivative of the position vector function. So what we need to do now is find this unit tangent vector's derivative. The derivative of the first component is a constant, so this is 0. And the derivative of sine is cosine, so this is cos t times that constant, which is 1 over rad 17. And the derivative of cosine is minus sine times the constant 1 over rad 17, so we just have rad 17 in the denominator. So the magnitude of this vector is going to be the x component squared plus the y component squared, so this is cos squared t over 17, plus the z component squared, which is going to be positive sine squared t over 17. And now let's simplify. Let's factor out the 1 over 17, which leaves cos squared t plus sine squared t, and again that's 1. So the magnitude of t prime is going to be just 1 over the square root of 17. So we have mag t prime. Now, we already found mag r prime. Let's remember what that was. Mag r prime was rad 17 times t. So now we're ready to put this together as a curvature formula that depends on the value of the parameter. Mag t prime is 1 over rad 17. Divide that by rad 17 times t, and we end up with a complex fraction where we keep the top, flip the bottom, so let's drop a 1 underneath the bottom in order to flip it to get 1 over rad 17 times t, and change that from divide to multiply so that we end up with 1 over 17 times t. And our formula for curvature that depends on the value of the parameter is 1 over 17t. Now, as a reminder, we could have used this formula as well, and we would have come up with the same function.